Okay, let's just summarize what we have done. Right, we have a picture of the atom. Right, there's a nucleus there. Of course, we don't know there's a neutron. From our experiment, we know that it's positively charged. Right, that's the conclusion. Very small nucleus surrounded by mostly empty space. A lot of empty space. Nucleus contain most of the mass of the atom. A nucleus that is positively charged. That's the conclusion we can come to from the experiment. Then we introduce the term of nuclide. Nuclide is basically to represent a nucleus, a group of atoms containing the same number of proton and neutron. Right? Then we come to nuclide notation. This is the mass number or nucleon number. This is atomic number or proton number. And then there's a chemical symbol. If it's positively charged, then you put a charge there, positive. Then we start nuclear fission, splitting of a large unstable nucleus into two smaller nuclei. Right? We can draw diagram, but usually drawing diagram takes a long time now. So we would rather represent it with a nuclide equation. That's a nuclide equation for this picture. And conservation of nucleon, that means left-hand side, you add this top number, superscript, and then add the right-hand side, superscript, it must be the same. There is three neutron here. And then conservation of charge, you add the bottom there, left-hand side 92, right-hand side also should be 92. You add up 92 also. Okay, so let us go to finish it off. Nuclear fusion. Small nuclide can react to release energy in the process called nuclear fusion. Right, your book is page 238. Nuclear fusion is defined as when two light nuclei, right, light nuclei join to form a heavier nucleus. This is heavier, these two are light. This process required extremely high temperature to maintain. Why do you need high temperature? Any idea?
Is it to let them move faster to collide each other?
In a sense, correct. We want them to move faster, but at the same time, remember the two nucleus, the two nuclei are positively charged. So as they come together, they are going to repel each other. So unless your speed is high enough, they will not collide. Right? So you want them to collide. So that's why you need high temperature. Right? This is why nuclear
So
fusion
can I
proven to be hard to produce on Earth. Very hard to produce on Earth because you want high temperature.
okay, so the reason for is the reason for why it need high temperature is because both of them are positive, so they repel, right?
They will
But we
repel,
need them
correct?
to collide. But we need them to collide. In that case, we only can use, just like give them more energy to move faster in order to collide, right?
That's right. They have both
Okay,
kinetic energy, so you are basically pushing them together to collide.
okay,
So you have to overcome that repulsive force. So that's why you need high temperature. High temperature will give them high kinetic energy. Okay with that?
okay, okay. Thank
Stars
you,
use
sir.
nuclear fusion to produce energy. In most stars, hydrogen atoms are fused together to form helium and produce lots of energy. So you have helium from the two hydrogen. Right? This is deuterium, form helium and then energy release. Energy produced during nuclear fusion comes from a small amount of particle mass being converted into energy. Right? What is happening? The total mass of this reactant, this helium, this deuterium, is less than helium. Sorry. Let me repeat again. The total mass of these two deuterium is greater than the mass of the helium. So the difference in mass appear as energy here. Albert Einstein described the mass energy equivalent with this famous equation, E equals to mc squared. E is the energy released from fusion in joule. M is the mass converted into energy in kilogram. C is the speed of light. Therefore, the mass of the
Excuse me,
product
sir.
is the product.
Excuse me,
Is the
excuse me.
product. Is the reactant. Right? It's less
Sir.
than the mass of the two original nuclei. Anything else? You're not clear?
It's like what is light? That's like light speed or what? The one
These two
light
are
speed.
deuterium. Deuterium.
I mean like what is light speed? Light speed.
Say again. Can't hear.
Light speed.
Light.
Uh, Light speed.
I'm not sure what you're talking about.
This one. Can I ask what is this?
The two light nuclei. These two must be light.
No, I meant about the speed of light. Speed of light.
Energy is produced. Oh,
Yeah, yeah. So what is the speed of light?
oh, speed of light is 3 times 10 to the power 8 meter per second. No?
Uh,
There's a constant.
okay.
That's a constant.
Oh,
So
okay, okay. Thank you, sir.
I thought you when you study electromagnetic waves, your teacher will have tell you that the speed of light is 3 times 10 to the power 8 meter per second.
Maybe I forgot.
Usually they will give you in exam.
Okay.
Okay with that? Anything else to clarify?
Nothing else.
Okay. So basically, as I've just said, the total mass of this reactant is greater than the mass of this product. So the difference in mass appears as energy. The amount of energy released during nuclear fusion is huge. The energy for 1 kilogram of hydrogen that undergoes fusion is equivalent to energy from burning about 10 million kilograms of coal. You can see that, right? Just 1 kilogram of hydrogen equal to 10 million kilograms of coal. It's just a small amount only. We produce so much energy. Okay. So we instead of drawing every time symbol like that, deuterium react with hydrogen to produce helium-3 plus energy. We will write the nuclear equation. Right? This is deuterium, this is hydrogen, this helium plus energy. Okay with that? Stop me if you are not sure or anything to
No
ask.
problem.
Okay, then
No problem.
make sure you know how to write the equation. Right? This is just for your info lah. Right? There's you don't need to know so far lah. But so far this is a suggestion by a scientist how the fusion reactor should look like lah. But anyway, this is for your info lah. It's right for info. It won't come out in exam. Okay, afterward there's a break. If you can try page 237, right? After this 40 minutes session, there'll be a 15-minute break. Right? Because I'm recording it, it has to convert. Then Zoom also want to have a little bit of break lah. So you can try page 237, or you can go and do whatever you want to do first. And then page 237, page 239 also. Okay, then I'll discuss with you if you have the time to do it. Okay, the next topic we are going to go is background radiation. Okay, as usual, this is the textbook that we are using. This is where I get the notes. If you want me to send you the notes, let me know. We are now coming to radioactivity, right? So we are now on page 230, background radiation. Right, that's the syllabus. Right, these are know the sources that make significant contribution to background radiation, including radon in the air, rocks and buildings, food and drink, cosmic ray. So these are the 4 areas that you need to remember lah. Anyway, you can look at the syllabus yourself during your free time. Okay, background radiation. Radon gas, don't bother about the 50%. I just know that radon gas is the major contribution. And then rocks and building materials, right, quite significant. Food, 11%. Cosmic ray, 10%. Others, 1%. Medical, medical will contribute about 13%. That one only if you are near, X-ray department in hospital or in university where there's a research in this area, then likelihood that you may be exposed. But in normal home, you won't be exposed to all that. Right? It's important to remember that radiation is natural phenomenon. That means occur naturally. Radioactive elements have always existed on Earth and in outer space. Right? It's there. We cannot control it. However, human activity has added to the amount of radiation that humans are exposed on Earth. Right? That's the one, medical one. Right? Human activity. Background radiation is defined as radiation that exists around us all the time. It's already there. Right? We are always exposed to it.
Excuse me, sir.
Say a bit louder.
Excuse me. Am I loud enough now?
Say a bit louder, can't hear.
It's like, can I ask, it's like, why food has radiation?
Food sometimes got carbon 14.
Uh,
Right? We will
okay,
go into that in a while. If you are a bit patient.
okay, okay, because got a little bit shocked to see even food also got radiation.
Yeah, food also got. Right? We will go over it first. And then after that, if you still find it confusing, let me know. Okay. So there are 2 types of background radiation. Natural sources, man-made sources. This is man-made medical. Every second of the day, there is some radiation emancipating, that means release from natural sources such as rocks, cosmic ray from space, food. Although most background radiation is natural, a small amount comes from artificial source such as medical procedure, including X-ray. This is where you go to hospital or a university where they have nuclear research there, then you are exposed to it. Levels of background radiation can vary significantly from place to place. Right? The idea that it can vary from place to place is because sometimes due to human activity, they may have transport radioactive material from one place to another. Right? It's probably found in sand. Certain places may have a lot of radioactivity. But radioactivity is something we cannot see. Unless we use a detector, we don't know it's there. Okay, that's what it means. Level of background radiation can vary significantly from place to place. Nuclear equation for nuclear fission is stated as that. Okay, can you calculate the number of neutron and emitted in this reaction? What is capital N?
Is it number? So, give me a second. Wait a while. Three. Three.
3 ah. Okay,
Three.
let's see. Conservation of nuclear number, you add the top there, no? 235 plus 1, and then 96 plus 137 plus n times 1, no? Okay, yeah, right. 3, good. Okay, let's carry on. Background radiation can come from natural source on Earth or space and make source, right? They can the background radiation can come from natural sources on Earth or space or man-made sources. Natural sources, radon in the air. Airborne radon comes from the ground. This is natural decay of uranium in rock and soil. The gas is tasteless, colorless, odorless, but not generally a health issue. It's just a gas. It's not a health issue. That's a radon. Okay, that is my master thesis on the research of working with this gas. You don't need to worry too much about that. This is alpha decay, deadline. Going to the left is beta decay. That one A level will require to be able to draw all this. So that is your uranium, 238, and then there's your radon. So uranium go into a series of decay. So this radon also is also radioactive. It will decay to polonium. Okay, so where can it be dangerous? Radon can be dangerous where it's in a storeroom where there's no window. Right? Because that radon, it can sneak in. It's a gas, it can go inside the storeroom. And then it will decay. And the dust will collect all the isotopes, the radioactive isotopes. And when you breathe in, you go into your lung. So that's the danger. That's why if you have a storeroom, it's better to once a while vacuum it or clean the dust away. Okay, so the second source is rocks and building. Rocks and building. Heavy radioactive elements such as uranium and thorium. Okay, I just refer to the previous slide again. Right? That uranium is radioactive. This is also radioactive. Right? That uranium is also radioactive. Right? So from rocks and buildings will be due to uranium and thorium. Uranium decays into radon gas, which is an alpha emitter. This is particularly dangerous if you inhale into the lungs in large quantity. Right? Remember, the radon gas is still radioactive and it disintegrates into other isotope, and that isotope will cling to the dust. That's why when you inhale, you breathe it in, it becomes dangerous because it accumulates in your lung. Natural radioactive activity can be found in building material, including decorative rocks, stone, and brick. Cannot escape. It's already there. Right? When we take the rock or stone or brick, it's already there. Cosmic rays from space. Sun emits an enormous number of protons per second. Right? Remember, protons are positive charge. Some of these enter the Earth's atmosphere at high speed. When they collide with molecules in the air, this leads to the production of gamma radiation. Other sources of cosmic ray are supernova and high energy cosmic event. Then we have carbon-14 in biological material. That means anything that is organic. All organic matter contains a tiny amount of C14. That means in our body also. Living plants and animals constantly replace the supply of carbon in their system Hence, the amount of carbon-14 in the system almost constant. Right? This is for your info. Right? From the sun, you got cosmic radiation. Cosmic radiation interact with nitrogen in the air, produce carbon-14. Right? Carbon-14 is radioactive. It mixes with the air, so the plants and grass will take in the carbon dioxide, and then the horses will consume the grass, and we will consume the fruits or vegetable. So we will take in the carbon-14. That's how the radioactivity enter our body. And then that 14 will decay by beta decay to nitrogen 14. Right? This is for info. Don't go too far. Radioactive material in food and drink. Naturally occurring radioactive elements can get into food and water since they are in contact with rocks and soil containing this element. Okay, because sometimes you have uranium in rocks, and then they may contaminate the food. Some food contain higher amount of potassium 40 in banana example. However, the amount of radioactive material is minuscule and is not cause of concern. So we don't have to have sleepless night lah, because the amount present is very little lah. Medical sources. In medicine, radiation is utilized all the time. Uses include X-ray, CT scan, radioactive tracer, and radiation therapy. Nuclear waste. While nuclear waste itself does not contribute much to background radiation, it can be dangerous for people handling it. Right? Nuclear waste is only for those who are handling it. Nuclear fallout and nuclear weapon. Fallout is the residue radioactive material that is thrown into the air after the nuclear explosion, such as the bomb that exploded at Hiroshima, right? Where we have nuclear weapon testing in the air. Then you have this radioactive material falling down on Earth. While the amount of fallout in the environment is presently very low, it will increase significantly in areas where nuclear weapons are tested. Right? If you are far away from where the nuclear weapon is tested, you don't have to worry. Just like last time when the French do some nuclear weapon testing in the Pacific there, New Zealand people are very angry. They send their ship there, right, to stop them. Nuclear accident. Accidents such as that in Chernobyl contributed a large dose of radiation into the environment. While these accidents are now extremely rare, they can be catastrophic and render area devastated for centuries. Right? So in a nuclear accident, it can be dangerous to people around them and the surrounding area, and that place there can be destroyed for centuries because it's radioactive. Okay, anything to ask before we carry on?
Is that actually does nuclear radiation is able to just like change DNA, just like have impact on DNA?
Yeah, that's the danger of exposure to radiation. Near the place is it will affect it will cause mutation to the DNA, which we'll come to it later on.
Okay.
Okay with that?
Yeah. Yes.
The sources that are most significant contribution are natural sources. Right? Radon gas, remember the 4 sources you need to remember: rocks and building, food and drink, cosmic ray. Right? Medical, you don't need to worry too much. Right? Make sure you remember this for your exam. Detecting radiation. It's important to regulate exposure of human to radiation. The amount of radiation received by a person is called the dose. Ionizing nuclear radiation is measured using detector connected to a counter. Right? We are now, if you want to refer to your textbook, it's on page 230. Count rate. Count rate is the number of decay per second recorded by the detector and recorded by the counter. Right? So the radioactive substance will emit radiation. So the radiation is the one that is detected by the detector. And then it will count 1, 2, 3, 4, 5. So it will be count per second or count per minute. No? Count rate decreases the further the detector is from the source. Remember, the source is a point source, so it emits radiation in all directions. So as you go further and further away, it becomes less and less, right? Because it's scattered into a bigger area. That's your Geiger-Müller tube, this one, the detector. This is the counter. Okay, so Geiger-Müller tube is the most common device used to measure and detect radiation. Each time it absorbs radiation, it transmits electrical pulse to the counting machine, right? So that's it detect in here, and then the electrical pulse will come out to the counter, and then this one will count. This make clicking sound or display as count rate. So either you design it to display the count rate, or you put a loudspeaker there. The loudspeaker will give a ticking sound where there's radiation. Okay, so in 5 minutes time, I will stop. Then we will wait for another 15 minutes while I convert the recording and then start new Zoom to you. You want to go for a quick drink, go ahead. The greater the frequency of tick or the higher the count rate, the more radiation the Geiger-Müller tube is absorbing. Therefore, it matters how close the tube is to the radiation source. Right? The closer it is, the more the count rate. The further it is, the less the count rate. The further away the source, the lower the count rate. Right? There are other radiation detectors. Photographic film often used in batches. People in hospital will wear this up, especially those who work in X-ray department. Ionizing chamber, there's ionizing chamber. Scintillation counter, spark counter. You just need to know the name. You need to know how it works. Right? Basic idea is radiation enter, it will ionize the gas. Right? For your ionizing chamber, and then you detect as a current. Okay, try this question. Geiger tube is used to detect radiation in a particular location. If it counts 16,000 decay in 1 hour, what's the count rate? Right? Give me the count rate in second.
4.44 count per second.
Right? Convert your 1 hour to 3,600. So the count rate is 16,000 divided by 3,600, 4.4. Is that right? Is that what you
Yes.
get?
Yes.
Okay, good. If asked if asked to name a device for detecting radiation, Geiger tube is a good example to give. You can refer to it as GM tube, GM detector, GM counter, Geiger tube. The examiner will allow a little bit of variation, but don't say radiation detector, right? Because it's two-way. It may be in the question itself. So they want you to tell GM detector, GM tube, or Geiger-Müller tube. Accounting for background radiation. background radiation must be counted for when taking reading in laboratory. This can be done by taking reading with no radioactive. Right? So what you do, you measure the count rate without the radioactive material. That's called the background radiation. Then after that, you measure the count rate with the radioactive source. Then you subtract the background radiation. No? Right? Let's look at this example. Then we'll stop for a while. A student is using Geiger counter to measure the count rate per minute at different distance from the source. The results of the graph, the results and the graph results are shown. Determine the background ready count. What is the background count?
I'm not sure about this.
Be a bit
Is
louder.
the back I'm not sure about this.
Okay, this one as you go further and further away, the amount detected, not radiation detected, is less and less. And then you can see after 1 meter, well, 1 meter there is constant. Means it's not detecting the radiation anymore. Radiation from the source. So this must be background. That one, background. Can
So the background is 1.15 counts.
when you count, you also will count from the radioactive source and the background. So as you go move away
Yes.
further and further from the source, after a certain distance, you can see that it's constant. So that means that from the radioactive source is normal already. Cannot be detected already because it's too far away. So it's detecting only background.
Okay.
Okay, I think we will stop here for a while. So I see you in 15 minutes time. You can try the question. Okay with that?
Okay, thank you, sir.